falling, not just a small little coil. So imagine this is 5 meters again. So 5 meters. Imagine from here to here is 40 centimeters. And imagine from here to here 60 centimeters. So now this is also falling. So calculate at any time the EMF induced in the rectangular coil and a rectangular wire. And we could also make a bunch of turns there. So we could say N is 10 turns. And the current is 1.2 amps. If we want, hey, we could even make add another effect. Let's say the current is going to the right, and let's say the current itself is non-uniform. Oh my gosh, 1.2 T, let's say 1.2 plus 0.6 T minus 0.4 T squared, some weird current function. So this is Faraday's law galore, right? All kinds of crazy things happening. So you have a current carrying wire. Its initial current is 1.2 amps to the right, but its current is changing. So eventually it looks like it's going to switch direction on you. So eventually as the T grows, the time is going to switch and it's going to go to the left, the current, you see. And then this is falling, right? I could make the height even bigger. Let's say it's 50 meters. Okay, let's see here. What kind of current? Well, in this one, since the current is doing some weird stuff, I don't even know what's going to happen because the current might switch directions. So this one is better if the math takes care of it, you know. So then I'm going to say what? Okay, so what is the EMF is going to be negative N d by dt BA. Oh, okay, here's one difference now with this than the other problem. The B field created across this loop is not uniform because this portion of the loop is closer to the wire than this portion. So I have to do an integral. So I have to take a slice of the loop. Then I have to say integral B dA, right? Then I have to integrate the B across the area of the loop because it's not uniform. So far, I've just been able to say BA, you know. Then I'm going to say negative N d by dt. What's the B? Mu 0 I over 2 pi r. Well, let's call it 2 pi y, right? But then that's negative because based on this, the field is into the board, right? The field is into the board. But that's, of course, when the I is positive. Then the field here is into the board. So then that's negative 2 pi y. And then dA is going to be the area of that. So it's going to be the length, 0.6 meters times dy. All right, so 0.6 times dy. Okay, then the two negatives cancel. Then I get EMF is N mu 0 over 2 pi, and then the 0.6 d by dt. Oh, the I also comes out. Oh, actually, hold on. The I comes out of the integral, but not out of the derivative because it's changing. So you see, you have a derivative of an integral here. So I comes out of the integral, but it stays here. I. And now the integral of dy over y. Okay, then you go like this. So now what's the limits of the integral? Well, at some random point, the wire is going to be here, right? So the distance from here to here is going to be y, right? So the limits of the integral are from y all the way to y plus 0.4, because it's 4.4 meters. This is 0.4 meters longer than that, right? So then you have 0.4, so y plus 0.4. Okay, so then I have here EMF. Mu 0 is 4 pi, so then that cancels and makes it 2 times 10 to the minus 7. N is 10 turns. Okay, then the current is 0.6 was the length. D by dt times I, and then this is ln of y plus 0.4, right? I'm just going to write it this way for now. Oh, you know what? I could just do it this way. Y plus 0.4 over y. Yeah, ln of y plus 0.4 over y. Okay, now we got like that. Now I have to take the derivative of that. You see, so what I have to do, what I had to do for this is first come up with an expression for the magnetic flux. What you're doing here physically is getting an expression for the magnetic flux through that rectangular coil at any instant. That's what the magnetic flux is. You see, it's the B times the dA, and you're integrating over the area of that rectangle. And now you're saying the magnetic flux is changing at a certain rate. So now you're taking the derivative of the magnetic flux. Okay, so now since the I is changing and the Y, you do the product rule. So you do 2 times 0.6 is 1.2, 10 times 10 to the minus 7, that's a micro. And then the derivative of that, so di dt times that, I'm just going to write it this way, 1 plus 0.4 over y. Yeah. 1 plus 0.4 over y. Plus I times the derivative of ln, which is 1 over 1 plus 0.4 over y. Right, so the derivative of this, so 1 over this, times the derivative of this, which is going to be negative 0.4 over y times dy dt. So a lot of stuff are happening here. To take the derivative of an ln function, you do 1 over this thing, which gives you this, times the derivative of this. And so since this is 1 plus 0.4 over y, then you take the derivative of this, you get 0. Then you get the derivative of this, which is negative 0.4 over y squared. Ooh, I made a mistake. Right? So the derivative of this is negative 0.4 over y squared times dy dt. Okay, now, okay. EMF 1.2 micro. Okay, now I could put my di dt, which is the derivative of this, which is 0.6 minus 0.8, 0.6 minus 0.8 t, ln of 1 plus 0.4 over y. plus y, which is that whole thing, and then you have here, you could distribute the y into here, so you have negative 0.4 over distribute the y, so you have y squared plus 0.4y times dy dt. Okay, so then of course we can use the expression y is equal to what was it, 4.9 t squared dy dt is equal to 9.8 t. Now in reality these aren't completely true because the current induced in this is going to be in a certain direction, right? And there's going to be a force on this, kind of opposing gravity due to the magnetic field of the wire. But that force is going to be so negligible in reality that it's not really going to be able to fight against the force of gravity. So for the most part, we can treat this as being the equation of motion of this wire, because that force created by that Lenz's law on this wire is very, very weak, right? So it can't fight the gravitational force. So again, we can answer any questions such as at any given time, how long, what is the EMF induced, or when it hits the ground, what is the EMF? Let's do the ground one. So when it hits the ground, what is the EMF induced at that instant? So then what will Y be? If the distance from the wire to the ground is 50 meters, then what will Y be when the object hits the ground? The Y will be 50 minus 0.4, right? So from here to here will be 50 minus 0.4, 49.6 meters. So if I want to know what the EMF is when the rectangle hits the ground, okay, so then 1.2 micro, wherever there is a Y, put 49.6. Okay, what will the T be? What will the time be? So then you could put here Y is 49.6, 49.6, 4.9 T squared, 49.6 divided by 4.9 square root. Okay, T is 3.182. Okay, so put that here, 3.182. And then put that in everywhere you see a T. Squared times negative 0.4. Okay, and then what's the velocity? Then the velocity is going to be 9.8 times 3.182. times 9.8. Okay, so then the velocity is 31.179. Okay, let's calculate that, and we should end with that. That's a good one to end with. Okay. So the EMF, again, step at a time, 1.2 micro. Okay, so then you're going to have 0.6. So I'm going to do the ln first. 1 plus 0.4 divided by 49.6. ln times parentheses 0.6 minus 0.8 times 3.182 close parentheses equals. Okay, so then I have negative 0.01562739 plus on the other part I don't have any ln, right? Yeah, I don't have any ln, so I just have 49.6 squared plus, ooh, that's a huge number, 0.4 times 49.6. Ooh, that one became really large. 2,480. Then on top I have negative 0.4 times 31.179. And now let's see what this top thing comes out. 1.2 plus 0.6 times 3.182 minus 0.4 times 3.182 squared equals. Okay, so now you got negative 0.9408496. So you see how I let all the negatives take care of themselves. So now what's going to be the answer? These two negatives will cancel and turn into positive. Oh, okay, so then this will be this like this, times 0.4 times 31.179 divided by 2480. It's positive, but then this is a bigger negative. So then negative 0.01562739. Okay, times 1.2. Okay, so the EMF is negative 0.01375 microvolts, which I could change to nanovolts, which is better. 1, 2, 3. So negative 13.075 nanovolts. Okay, that means at that instant in time, let's see here what's going to happen. What's the direction of the, if it's negative, what's the direction of the current? What's the direction of the current flow through the wire? If it's negative, that means it's going this way. Could we make sense out of that with the right-hand rule? So if it's negative as it hits the ground, it's creating a B field into the board. Does that make sense? Well, at that instant, what is the current in the wire? At that instant, what is the current in the wire? Let's see. What was the time? The time was 3 seconds. 1.2 plus 0.6 times 3.182 minus 0.4 times 3.182 squared. Okay, the current has already flipped 0.94 amps. So by the time that this guy has hit the ground, the current has flipped to the left, which means what kind of field is it producing? It goes like this, and then it's producing a B field out of the board. You see, it's producing a B field out of the board. Oh, let's see. And then what's happening as it's falling, those B fields are getting weaker. Okay, but then what's happening to the current? What's the derivative? di dt. Di dt is the 0.6 minus 0.8 t. So this is the di dt right here, which came out negative, right? So the current came out negative. The rate of change of the current came out negative. Remember, it was negative 3, was it? I wrote it somewhere. I can't find it. I can't find it now, but it was negative 3 or something. Negative 0.6 minus 0.8 times 3.182. Okay, negative 1.9456. So what does it mean if the current is negative? If the current is negative and the rate of change of the current is also negative, that means the current is not only to the left, but it's actually growing. It's getting larger, right? So the current is to the left and its value is 0.94 amps. And the rate of change of the current is also negative, which means the current is getting larger to the left. So what does that mean? The B field that it's producing is getting larger. It's getting out of the board and it's getting larger. So then what kind of current should you create? You should create a current that's opposing that, right? Even though you're moving into weak areas of weaker field, but the current is getting larger and larger. So what was the answer we got for the direction of the current? Clockwise, right? Yeah, it's negative. That makes sense. So the direction of the current you're producing is clockwise to fight against the field that is out of the board, and it's getting larger and larger because the current is growing. Even though you're still moving away from it and you're going into regions of weaker field, but since it's getting larger, you're still going to try to fight it. You see that? So it's kind of interesting that the whole science did work out, and we are able to actually explain that by the physical significance of what's happening. Okay, guys, that is the chapter on Faraday's law. Lots of different situations that we saw Faraday's law can be useful for.